Hi there, my name is Dmitry and I welcome you on my technical channel. We continue our workshops dedicated to the MPSoC Zynq7000 from Xilinx, and more specifically RT-Z7 platform. Today we are going to talk about the Ethernet interface and ways of configuring it. When it comes to hardware of the Ethernet interface, there are usually three different subcomponents. One is MAC, which is medium access control. It is block of hardware, usually part of MCU, CPU, FPGA, ASIC, whatever. In our case, it is a part of MPSoC from Xilinx. MAC interfaces directly with an Ethernet PHY. Ethernet PHY is a dedicated chip. In essence, it is a transceiver which interfaces directly with the physical layer of the network. When it comes to data communication between MAC and PHY, there are several interfaces available, as you can see: MII, RGMI, RMII, GMII. But also, there is a separated interface which allows MAC to configure PHY. The interface is MDC MDIO. So what is the need in configuration of Ethernet PHY? Well, we need to instruct it at which speed it is going to operate. It can be either 10 megabits per second, 100 megabits per second, or 1 gigabit. So from the MAC layer, we instruct the PHY to operate at a specific speed. It can also be auto-negotiation. And we configure its internal clocks. Also, Ethernet PHY can notify the MAC layer about link up and link down events. From electrical point of view, there should be two physical lines dedicated to the MDC MDIO communication. When it comes to software, the eMAC driver usually has a specific logic of communicating to a specific type of Ethernet PHY. Now, going back to our hardware platform, we can see that a chip from Realtek is used as an Ethernet PHY. Going to the MDIO MDC interface, those two lines are connected to our MPSoC. Let's have a look. Ethernet MDC, Ethernet MDIO, MIO 52, MIO 53. When it comes to MPSoC from Xilinx, there are two different types of GPIO, general purpose I/O pins. Those are MIO pins and EMIO pins, and they not interchangeable. And if pins are not interchangeable, it means there might be some challenges when it comes to electrical design and software implementation. So let's have a look at the actual project to understand what kind of limitations are there. Let's switch to a slightly different view. I'm going to extract my project, which is called MDIO over GPIO, and then I'll explain this name a little bit later. Let's create a Vivada project and build it. As always, it takes some time. project is successfully created. Let's open it in Vivado. Again, you can see that the project is created for RTZ7 platform. Let's open block design. You can see there is only one IP block, which is processing system. Double click and see how the interfaces are configured. MIO configuration. So we are looking at IO peripherals, Ethernet 0, MIO 1627. Let's double check it. Ethernet interface, MIO 16 to MIO 26. That's exactly right. And if you noticed, I have MDIO interface disabled, which was done intentionally. I'll explain a little bit later, but for now, let's have a look that the only options that we have is we can use MIO 5253 or we can use EMIO pins. EMIO pins are so-called PL, programmable logic pins, and they are not controlled by the PS half of the MP sock. Also, MIO pins cannot be controlled by PL logic. Again, we can double check this statement by going to the Zynq forum. And then they explicitly say MIO pins have dedicated connections to PS subsystems. They can't be connected directly to the PL fabric. So now imagine that for some reasons during our design stage we couldn't use MIO 52 and 53 for some unbelievable reasons. Instead, we routed those MDIO MDC lines to some random MIO pins. And this in essence means that the MAC driver won't be able to talk to the PHY chip. This example demonstrates how to overcome this limitation and then how still, make it possible to communicate to the PHY chip when it is connected through any random MIO pins, or actually EMIO pins are also part of it. So once again, I would like to highlight with this option unticked, there is no way to communicate it the standard way from eMAC to the PHY chip. Nevertheless, we leave it as it is and build the project. Run synthesis. Two critical warnings. I mentioned them in my previous video. Let's not focus on it. Yes, the synthesis is still running. It's not blocked by those two warnings. Successfully completed. Run implementation. And I'm going to stop my camera in order to not make it way too boring. Successfully completed. Generate bitstream. Successfully completed. Export hardware, include bitstream, choose location, and we have experiments, MDIO over GPIO, MDIO over GPIO project. Complete. Let's check. Let's go to SDK and MDIO over GPIO. We have successfully generated HDF file. Now we can create SDK project. Again, it should take several minutes, so I'm going to stop my camera. The project is successfully created and built by the look of things. Let's check the left. Yes, FSB was built, and then the application itself is successfully built. Let's open it in IDE. Close the welcome page. We can see that there is no errors. Let's check build automatically, and first time it is going to build it anyway, or rebuild after running TCL scripts. That's the funny behavior from Vivado and Zynq. Meanwhile, let's have a look at the project itself. This is the entry point. The application is written in FreeRTOS, as you can see. So what it does upon its start, it configures the network interface, including LWIP stack, TCP/IP stack. There is a static IP address, and because of that, we need to configure appropriately the network adapter on our PC, which I'm going to show you how it is done. But in essence, what happens, it starts the EMAC interface in a separate thread, and then it starts our echo daemon. So this is the core functionality that we were going to replace. As you remember, there is no way for us to communicate over standard MDIO MDC hardware block because we haven't even activated it. Instead, we have a driver which is a software implementation of MDIO protocol. So it is a bit banning mechanism, bit banning way of talking to PHY through any of our nominated GPIO pins. And in our case, as you can see, we chose MIO 55 and MIO 53. This is a part of a GPIO driver, which allows to use MIO pins or EMIO pins. Doesn't really matter. From the driver point of view, it is exactly the same way of driving them. But our interface is physically connected to MIO pins, so we have no choice but to use MIO 52 and 53 only, just because of the way how our hardware platform is configured. Okay, let's go back to our application. There is a simple echo service which listens on a TCP port 7 just to prove that the network interface is up and running and it is fully functional. So that's about it. let's try to run this application, and then I'll explain in details how it works. First of all, we need to start terminal application. And I'm going to switch the camera. So as you can see, the board is already powered. I'm going to connect network. You can see it started blinking already. Well, let's have a look at the network. So now I'm going to check my settings. Ethernet, adapter options, Ethernet properties. You can see that it is configured with the static IP address. The address is 9.1, and then if we go back to our development board, it is going to be configured as 9.10. So they're not gonna conflict, but at the same time, they are in the same subnet. So let's try to run the application and see what happens. Standalone application, reset entire system. And we used our own application, CPU 0. Let's pick release and try to run it. Waiting for PHY to complete auto negotiation. It detected auto negotiation complete, as you can see, and it detected our RTL Realtek chip, PHY chip. So now what we can do, we can try to pin 10, and then you can see the board is responding, right? Okay, let's try to access the echo server, and again it is accepted, and then the each character comes back in the form of echo. So we definitely successfully configured the Ethernet interface, and we established communication. Now, to prove that now we actually working through our software implemented MDIO MDC interface, first of all, let's log some debug info printf, and let's say that it is for writing, and this is for reading. Let's switch to release, build. Let's try to run it again. As you can see, the Emac driver is definitely accessing our logic. Now, to prove the point, let's do it this way. Rebuild. And run again. It tries to read. Maybe we should do it in a slightly different way. We need to remove debug info and rebuild. Start finding auto negotiation. And then you can see it's not negotiating. We can try to ping, obviously nothing happens. The interface is down. So, how did we manage to patch the Emac driver, which is part of board support package, and remap it to our own functions for reading and writing MDIO, MDC registers? Let me show you. We have patches in this folder, and then this is actually where we remap phi write and phi read functions to our own implementation. So what we do while we are in the middle of building process, we simply replace the original files in BSP package with our own versions. Emac PS control. And this is the way, so this is the way how we did it, how we managed to remap it to our own version. Yeah, so it is obviously not negotiating, as you can see. So I just proved the point that we work indeed through a software implementation of MDIO protocol. So that concludes the workshop for today. If you would like to get full access to the project, to this project, please follow the link below this video, visit our website and buy the full package. By doing so, you support us and you motivate us for the next developments. But if for any reasons you don't want to buy this project, you can obviously spend some time and implement it by yourself. And by doing so, you will improve your knowledge in this area. So please hit a subscribe button if you like it. Please like this video if you like, or dislike if you didn't. And see you next time. Bye.